Okay, hi everybody. Welcome to this week's Q&A video, although there weren't really any Q's this week, so I don't have many A's to give. It's fine if you didn't have questions this week, but just a reminder that you don't have to have a specific question in order to post in the discussion board. It's just as useful, maybe even more useful to me to hear I don't have a specific question, I just don't understand this topic, or this lecture was really confusing. Um, could you go over this thing again? Because that allows me to tailor these videos. I can, explain something in a different way or find a different example, because it's more difficult to get feedback in this online format. It's really important to me that I know, how you're feeling about the material. Okay. But I'm still going to use this video to talk about a tool that is kind of up and coming in econometrics and can be really useful to you, especially in the early stages of a research project. And that's what are called directed acyclic graphs, or sometimes that's abbreviated as DAGs. Okay. And so a graph, let's start with the graph part. In graph theory, which is a section of mathematics, all you need to have a graph are what are called nodes, which you can just draw as circles. So that's a node. We'll call that node A. And this is node B. Okay, so nodes and also edges, which connect nodes. Okay, so this is just a graph. What makes something a directed graph is that we still have our nodes and we still have our edges, but the edges indicate some direction. Okay, so rather than just connecting A and B, this time the edge is showing that something is starting in A and affecting B. Okay, and in order for it to, so that's a directed graph. And acyclic just means that you can't have it look like this. Where you've got a direction going from A to B, then going from B to C, then going from C to A. So you can't have that. Okay, so that's a directed acyclic graph. Okay, why does this matter for econometrics? Well, for econometrics, we have the graph, the nodes represent variables. So, for example, from class, we had health, and we had hospitalization. Okay, so the nodes are our variables. All right. And the edges are causal effects. So this is saying hospitalization causes health. Okay, so that's a really basic way of showing a causal relationship using a directed acyclic graph. All right, but this seems kind of basic. All right, how can we use this to demonstrate how we could be careful in our research design? Well, let's look at an example from last week's lecture. Right, we were interested in the effect of corporal punishment on adult behavior. Okay, And we know that there's some causal effect here that we're interested in. Okay. And this another word of this causal effect, another way we can say that is that there's a directed path from corporal punishment to adult behavior. Okay, so another word for a causal effect is a directed path. Okay, and what we talked about is that there's probably a third variable that's going to causally affect both corporal punishment and adult behavior. Okay, and that is probably childhood behavior. Right, this is the idea that rotten kids are more likely to get spanked. That's this causal effect. And rotten kids grow up to be rotten adults. So that's this causal effect here. Okay, and so a piece of terminology that is helpful is that there are directed paths, which are indicated by arrows, but there are also just paths. And a path is just, are there edges connecting one variable to another regardless of their direction? Okay, so there are actually two paths from corporal punishment to adult behavior. All right, there's the first one that we already see. That's the directed path. Okay, but there's another path that goes this way. All right, remember, paths don't, the arrows don't matter for finding paths. Arrows matter for directed paths, but paths occurred regardless of the arrows. Okay, so we go from there's a path from corporal punishment to childhood behavior, and there's a path from childhood behavior to adult behavior. Okay, so that's our second path. Okay, and another word for this path here is what's called a backdoor path. Okay, and why does this matter? Well, sorry about that. The correlation between two variables I guess you could say the raw correlation between two variables is the combined effect of all paths, not all directed paths. Okay. What that means is that, there was that study we talked about in the annual review of pediatric medicine or whatever, where they found that corporal punishment was correlated with adult antisocial behavior, right? But that correlation, it's not just this effect here. It's kind of the sum total of this effect and this effect, or this path here plus this path here. Okay, so that's this is kind of how you can demonstrate omitted variable bias. Okay, omitted variable bias is basically saying there's a backdoor path connecting one of our variables to another of our variables by means of a third variable. Okay, and so another example that we'll talk about at length is, let's say we have education and we have income. Okay, how much does going to school raise your paycheck by? Angrist talked about this in one of his videos. Okay, and we know that there's an effect here, right? Education causally affects income. Okay, but we think that there's some third variable, some omitted variable, that might causally affect education and causally affect income. And econometricians typically call this variable ability. You know, basically just how smart are you, right? Smarter people are better workers, smarter people are better students. And so when we're looking at the correlation between education and income, we're not just seeing this path, we're also seeing this path, the backdoor path by way of ability. Okay, and so the solution to omitted variable bias, which is also just called confounding. So this variable here, ability, is also called a confounder, is to condition, sorry, I'm still figuring out this drawing tablet I got, to condition on the omitted variable. Okay, and so what that means basically is that we want to only compare individuals with equal levels of ability. So maybe take a sample of people all with the same SAT score, and then look at the correlation between education and income. And when we do that, when we condition, we kind of can draw a box around it. And when we condition on a variable, that blocks out the backdoor path. Okay, so if you have a confounder, if you draw out your graph and you find that, you know, there's a confounding variable in your, you know, that's muddying up the causal relationship you're trying to estimate, the solution is to condition on that omitted variable. Okay, but that doesn't mean we should always condition. So another example, let's draw a different directed acyclic graph here. Let's talk about the gender pay gap, which is very common. We've got your sex, you know, whether you're male or female. We have your income. All right, and we think there is some causal effect of sex on income. Okay, maybe employers are discriminating against women. Okay, and there's a third variable that people are interested in, that's your hours worked. Okay, how many hours do you work per week, right? And most people draw the directed acyclic graph of this relationship like this, where women work more hours and working more hours causes you to earn less income. Part-time workers earn less than full-time workers. Okay, so you can see here that there are two paths, right? There's the direct causal effect that we're interested in, and there's this backdoor path. Okay, and so the solution would be to condition on this variable to better understand what the actual effect of discrimination is. All right, the thing is, this isn't the only way we can draw the graph, can we? Okay, so this is hours worked. It's true that hours affect income, but it's also true that income, you know, the amount you're earning at your job, might affect how many hours you're working. Okay, if you're you know, this is basically just a labor supply curve, right? If you're making $10 an hour, you'll probably work fewer hours than you will if you're earning $20 an hour. Okay, so now the graph looks like this. Okay, and so now we have a special word for this variable here. We call it a collider. All right, and the reason we use that terminology is because you can think two causal effects are colliding at this variable. All right, and what's important about that is that conditioning on a collider creates, what the heck? Why did I put an H there? Sorry. Creates paths that previously didn't exist. In other words, it creates bias. So this is called collider bias. One way to think about collider bias is we can do this with a scatter plot. So let's say we have two variables, you know, A and B. Okay, and the scatter plot for A and B looks like this. Trying to make this as clear as possible that there is no relationship between A and B. Okay, and then we create a new variable C, and we'll say C equals 1 if, or CI equals 1 if AI plus BI is greater than, you know, some constant n. Okay, so that would be if we, you know, draw in the constant A. So basically, if A plus B is big enough, then C is going to equal 1. So all of these dots here will say would have C equal to 1. Okay, and so if we were to draw a directed acyclic graph, right, we'd have A and B. There's no causal relationship between A and B. We're looking at it like they're not related at all, but they do both affect C. So this is probably a better way than using this equation. Okay, basically, if you have a low B or a high A, then C is true. Okay, but if we were to look at, you know, just the red dots, we would see that there is a relationship, right? There's a very clear upward sloping relationship. So if we condition on C, we would find a positive relationship between the two variables where there wasn't one before. Okay, and that's why we don't want to condition on a collider, right? We'll talk more about what exactly conditioning is in 2 weeks when we talk about multiple regression. But for now, it can just help you to, you know, draw out your graphs and figure out, okay, what are my confounders? What are my colliders? And that'll help you know, what am I going to control for? So already, hopefully, you're thinking about your final research paper. I don't expect you to be like gathering data or anything, but just thinking like, hey, what am I interested in? And one thing that can be really helpful is to draw out, you know, the variables that you're interested in and think about confounders, think about colliders, because that'll tell you what you also need data on. All right, so if you can, you know, draw out your graph and say, hey, this is a really important confounder, then you should look for data that not only has your independent and dependent variable, but also data on this this confounder. Okay, so that's just a really basic introduction to directed acyclic graphs. Again, don't hesitate to ask more questions. I hope you have a great weekend.